Searching an ordered array. With an ordered array, however, we can stop a search early even if the value isn't contained within the array. Let's say you were searching for a 22 within an ordered array of 3, 17, 75, 80, 202. We can stop the search as soon as we reach the 75, since it's impossible for the 22 to be anywhere to the right of it. Now this is the implementation of this. First, we define the function linear search, and then we have a parameters array and then search value. Then we iterate through every element in the array via array.each underscore with underscore index do to its element and index. If we find the value we're looking for, we return its index. If element is equals to search value, return index. If we reach an element that is greater than the value we're looking for, we can exit the loop early. So if you reach the element that is greater than the value we're looking for, else if element's greater than search value, exit the loop by breaking it through break and end. And then we return nil if we do not find the value within the array. Return nil if we're able to search it all the elements and nothing there comes up, or the search value did not come up. Now this method accepts two arguments. Array is the ordered array we're searching, and the search underscore value is the value we're searching for. Here's how to use this function to find the 22 in our example array. So p and then the linear underscore search function and the array 3, 17, 75, 80, 202 and the search value 22. As you can see, this linear search method iterates over every element of the array looking for the search underscore value. The search stops as soon as the element it's iterating over is greater than the search value, since we know that the search underscore value will not be found further within the array since it was an ordered array. In this light, linear search can take fewer steps in an ordered array than in a classic array in certain situations. So the linear search operation or linear search algorithm rather takes fewer steps in an ordered array than in a classic one. That being said, if we're searching for a value that happens to be the final value or not within the array at all, we will still end up searching each and every cell. So if it's a final value or the value is not in the array itself, therefore it will take worst case scenario n number of elements or n steps for us to iterate to those array. It will take n steps in both arrays for worst case scenario. However, linear search is only possible algorithm for searching for a value. Now there comes binary search. So binary search could be thought of as a guessing number game when you were a child. So here's an example. Guess which number I'm thinking of. You immediately intuitively know that you would guess it from the middle for you to eliminate half of the possible values for you to be able to guess it in a few number of steps. So step 1, we begin our search from the central cell. We can immediately jump to this cell since we can calculate its index by taking the array's length and dividing it by 2. So we can go to this index because we know the array's length. So if you divide that by 2, you will be able to go here on this data part of the computer or cell part of the memory. We check the value at this cell, and we saw that it's 9. Because the value uncovered is a 9, we can conclude that the 7 is somewhere to its left. We've just successfully eliminated half of the array cells, that is all the cells to the right of the 9 and the 9 itself. Step 2, among the cells to the left of the 9, we inspect the middlemost value. There are 2 middlemost values, so we arbitrarily choose the left one. So let's say we just choose, there's 2 value. Let's say our code will gonna choose the left one. We saw it's a 4. So the 7 must be somewhere to its right. We can eliminate the 4 and the cell to its left. So if we implement this to our code, let's say if it's greater, turn the pointer to the right? Step 3, there are 2 more cells where the 7 can be found. We arbitrarily choose the left one as shown in the image on page 20 on this. So we saw it's 6. Step 4, we inspect the final remaining cell. If it's not there, that means there is no 7 within this ordered array. But it turns out there is. So here's an implementation of the binary search in Ruby. We define the binary search function with the parameters array and search value. First, we establish the let's just make it bigger. First, we establish the lower and upper bounds of where the value we're searching for can be. To start, the lower bound is the first value in the array, while the upper bound is the last value. So lower underscore bound equals to 0, upper underscore bound is array.length minus 1. We begin a loop in which we keep inspecting the middlemost value between the upper and lower bounds. While lower underscore bound is less than or equal upper underscore bound do. So that's how we begin a loop in which we keep inspecting the middlemost value between the upper and lower bounds. While lower underscore bound is less than or equals to upper underscore bound do. And then inside this while loop, we will find the midpoint between the upper and lower bounds. We don't have to worry about the result being a non-integer, since in Ruby, the result of division of integers will always be rounded to the nearest integer. Now midpoint equals to upper underscore bound plus lower underscore bound over 2. And then that's what we use. We inspect the value at the midpoint. Value underscore at underscore midpoint is equal to array midpoint. If the value at the so that's the code for us to inspect the value of the midpoint. We put that in an array. If the value at the midpoint is the one we're looking for, we're done. If not, we change the lower or upper bound based on whatever we need to guess higher or lower. If search, so using if statement, if else, if search underscore value is equals to value underscore at underscore midpoint, return midpoint. Else if search underscore value is less than value underscore at underscore midpoint. So this is so if it's less than, upper underscore bound is equals to midpoint minus 1. So this is actually we turn to the left if it's less than. Else if search value is greater than the value underscore at midpoint, lower underscore bound equal midpoint plus 1, which is turned to the right. We change the midpoint to the right, and then end. And so if we narrow the bounds until they've reached each other, that means that the value we're searching for is not contained within this array, and we return nil and end. So as with linear search underscore search method, binary underscore search accepts the array and the search value as arguments. So as in linear search, it also accepts array and search value as parameters or arguments. Here's an example of how to call this method. P binary underscore search 3, 17, 75, 80, 21. So it's the same as linear search. And also it's in Ruby. So the method first establishes the range of indexes in which the search value might be found. We do this with lower underscore bound equals 0, and then upper underscore bound equals to array.length minus 1. So it established the range of indexes for that specific array, or in this specific input of data and functions that we're creating. Because when starting our search, the search underscore value might be found anywhere within the array. We establish the lower underscore bound as the first index and the upper underscore bound as the last index. So because the search value might be found within the array that we are creating, or we establish the lower underscore bound as the first index and the upper underscore bound as the last index in the array. So array.length minus 1 because it starts with 0. The essence of the search takes place within the while loop. So the search operation takes place within the while loop. While lower underscore bound is less than or equal upper underscore bound, these loops run while we still have a range of elements in which the search underscore value may lie. So again, it runs while we still have a range of elements in which the search underscore value may lie. So the keyword here is while range of elements. As we'll see shortly, our algorithm will keep narrowing this range as we go. The clause lower underscore bound less than or equal upper underscore bound will be reached when there's no more range left. So our algorithm inside this will keep narrowing this range as we go. So this initial ranges or initial range where we search the lower underscore bound and upper underscore bound will keep narrowing as we go. The clause lower underscore bound less than or equal upper underscore bound will be reached when there's no more range left, and we can conclude that the search underscore value is not present in the array. So this, when lower underscore bound is less than or equals to upper underscore bound, means that there's no more value to search. Therefore, we have to return nil. Within the loop, our code inspects the value at the midpoint of the range. This is accomplished with, so it finds the midpoint within the range using midpoint equals open parenthesis upper underscore bound plus lower underscore bound close parenthesis over 2 and value underscore at underscore midpoint equals to array midpoint. So we put the midpoint to the array using a new variable that we created, value underscore at underscore midpoint. Now the value underscore at underscore midpoint is the item found at the center of the range. Now, if the value underscore at midpoint is the search underscore value we're looking for, we've struck gold and can return the index in which the search value is underscore value is found. So if then inside after that initialization of variable, we use if statement. If search underscore value equals to value underscore at underscore midpoint, return midpoint. Now, if the search underscore value is less than the value underscore at underscore midpoint, it means the search underscore value must be found somewhere earlier in the array or the left of the array. We can then narrow the range of our search by making the upper underscore bound the index to the left of the midpoint. So else if search underscore value is less than value underscore at underscore midpoint, we change the upper underscore bound value at the initial range we created equals to midpoint minus 1. So that's the new upper bound. Since the search value underscore value cannot possibly be found anywhere further than that. Conversely, if the search underscore value is greater than the value underscore at underscore midpoint, it means the search underscore value can only be found somewhere to the right of the midpoint. So we raise the lower underscore bound appropriately. So as you notice, for less than or on the earlier array, we change the upper bound. But if it's the more latter part of the array or on the right of the array, we change the lower bound, which is the initially index 0. So else if search underscore value is greater than value underscore at underscore midpoint, lower underscore bound equals to midpoint plus 1. We return nil once the range has been narrowed down to 0 elements, and we know with certainty that the search underscore value does not exist within the array. So if the range is no longer more than 0 elements, therefore we narrow down and we did not find our request. So that's where the nil will comes in. So that's while so we return the null. So binary search versus linear search. The pattern that emerges is that for each time we double the size of the ordered array, the number of steps needed for binary search increases by 1. This makes sense as each lookup eliminates half of the elements from the search. So keep in mind that ordered array, so here's the graph for linear search. So as you can see, it's enormous difference in performance as data increases. Keep in mind that ordered arrays aren't faster in every respect. As you've seen, insertion in ordered arrays is lower than in standard arrays, as the regular arrays insertion doesn't require a search at all. So an ordered array, it's kind of like the same as duplicate array, in which you have to search for insertion before you can insert it. So it's lower when it comes to insertion compared to classic array. But for searching operation, it's enormously fast. But here's the trade-off. By using an ordered array, you have somewhat slower insertion but much faster search. Kind of like the same with how the search algorithm works today. We have like an enormous great search algorithm power, but people really don't or really know their search queries. So what you have to do is to provide an initial request or initial idea for them to search. Kind of like minimizing the blank state as a design principle we've discussed in the previous video. Often there is more than one way to achieve a particular computing goal, and the algorithm you choose can seriously affect the speed of your code. It's also important to realize that there usually isn't a single data structure or algorithm that is perfect for every situation. For example, just because ordered arrays allow for binary search doesn't mean you should always use ordered arrays. In situations where you don't anticipate the needs to search the data much, only adding data, standard arrays may be a better choice because their insertion is faster. And as we've seen, the way to analyze competing algorithms is to count the number of steps each one takes. Oh yes, big O notation. So we're gonna discuss this now on how we actually measure the speed using big O notation. So it came from mathematical concepts. So here, to help ease communication regarding time complexity, computer scientists have borrowed a concept from the world of mathematics to describe a concise and consistent language around the efficiency of data structures and algorithms, known as Big O notation. This formalized expression of these concepts allow us to easily categorize the efficiency of a given algorithm and convey it to others. Like linear search takes n steps for n elements in the array. So it's a formalized expression for the computer scientists to better express these concepts of computers that allow us to easily categorize the efficiency of a given algorithm and convey it. Like linear search takes n steps for n elements in the arrays. So how can we put that into more expressive so that we can easily convey it, the steps, to others? While big O notation comes from the math world, I'm going to leave out all the mathematical jargon and explain it as it relates to computer science. A. Big O, how many steps relative to n elements? In a worst case scenario, linear search will take as many steps as there are elements in the array. As we previously phrased it, for n elements in the array, linear search can take up to n steps. So, the first concept of big O that we're trying to know is how many steps relative to elements. So usually we measure that using worst case scenario. So let's say there's an n elements, though in some cases it could be an O1 or O of 1 speed. We measure that using worst case scenario. The appropriate way to express this in big O notation is ON. Some pronounce this as big O of n, others call it order of n. My personal preference, however, is O of n. It expresses the answer to what we call the key question. The key question is, if there are n data elements, how many steps will the algorithm take? The answer to the key question lies within the parentheses of our big O expression. ON says that the answer to the key question is that the algorithm will take n steps. Let's quickly review the thought process for expressing time complexity with big O notation. Again, using the example of linear search, first we ask the key question. If there are n data elements in array, how many steps will linear search take? Because the answer to this question is that linear search will take n steps, we express this as ON. For the record, an algorithm that is ON is also known as having linear time. Let's contrast this with how big O would express the efficiency from reading from a standard array. As you learn in why data structures matter, reading from an array takes just one step, no matter how large the array is. To figure out how to express this in big O terms, we're going to again ask the key question. If there are n data elements, how many steps will reading from an array take? The answer is that reading takes just one step. So we express this as O1, which I pronounce O of 1. And this is why O1 is considered the fastest kind of algorithm. Even as the data increases, an O1 algorithm doesn't take any additional steps. The algorithm takes a constant number of steps no matter what n is. In fact, an O1 algorithm can also be referred to as having constant time. One way of describing big O is that it describes the upper bound of the growth rate of a function. So this is kind of mathematical way to describe it. An upper bound of the function, which is really the upper bound, like the array, binary search array we mentioned, or that if a function gx grows no faster than a function fx, then G is said to be a member of OF. So, meaning if this grows no faster than this as data increases, it means that we categorize that as OF. Kind of like the 2n, or the constant, which we're gonna discuss later, does not matter in grand scheme of things when we're categorizing different speeds of algorithm. What matters is that as the data increases, we don't see significant increase with that constant along with that for example, an O1 and an ON. So an O1 will always be faster code in any computers, in any people that using it, because of that category of the time complexity. So it's really faster no matter how many multiply of constants you put. Depending on your mathematics background, that either makes sense or doesn't help very much. So that's why we're not discussing mathematical equations here, because it could be confusing depending on your mathematical background. So the soul of big O. Well, big O is an expression of the number of an algorithm steps relative to n data elements. That alone misses the differ y behind big O. What I dub the soul of big O. The soul of big O is what big O is truly concerned about. How will an algorithm's performance change as the data increases? An algorithm that is ON, on the other hand, is a different type of algorithm compared to O1, just like this. O1, as the data increases, it's the same speed. However, here, it's the same steps. Here, the steps increase as the data increase. So sometimes for a data set that is fewer than a certain number, like 100 elements, an ON algorithm takes fewer steps than the O1, 100-step algorithm. At exactly 100 elements, the lines cross, meaning the two algorithm takes the same number of steps, namely 100, but here's the key point. For all arrays greater than 100, the ON algorithm takes more steps. So does that mean that in every cases, like best case, worst cases, and average case, ON is always faster than O1 category? No, as you can see here, the ON is faster in less than 100. But as data increase, the 100 or O1, because we don't really care about constant, is faster. The same is true even for an O1 algorithm that always takes 1 million steps. As the data increases, there will inevitably reach a point at which ON becomes less efficient than O1 algorithm and will remain so up toward an infinite amount of data. As you learned in the previous chapter, linear search isn't always ON. It's true that the item we're looking for is in the final cell of the array. It will take n steps to find it. So a linear search isn't always ON. It's true that if the item we're looking for is in the final cell of the array, it will take n steps to find it. So if it's in the final stage, it will take n steps to find it. But when the item we're searching for is found in the first cell of the array, linear search will find the item in just one step. So this case of linear search would be described as O1, which is the best case. So this is the soul of big O. It's that there's a different scenarios in different category. So in the best case scenario for linear search, it's O1, and the worst case is n steps. And remember, sorry about that. Sorry about that. So, and remember, initially we tried to measure every algorithm using its worst case scenario, because if we are prepared or we know that it is what will happen in worst case scenario, we are confident that it will not go over that worst case scenario. So this is a case of linear search would be described as O1. If you were to describe the efficiency of linear search, in its totality, we'd say that linear search is O1 in a best case scenario and ON in a worst case scenario. Same algorithm, different scenario. So that's where our best case, where average case and worst case scenario came. While Big O effectively describes both the best and worst case scenarios of a given algorithm, Big O notation generally refers to the worst case scenario unless specified otherwise. This is why most references will describe linear search as being ON even though it can be O1 in a best case scenario. So Big O notation again generally refers to the worst case scenario unless specified otherwise. That is where further analysis comes. That's why we also need to determine the goals and our specific goals if that different scenario will gonna matter, because if we're trying to optimize our application for searching at the initial index of our array, then a linear search would always conduct a O1 speed or O1 steps, while Big O effectively describes both the best and worst case scenarios of a given algorithm. Big O notation generally refers to the worst case scenario unless specified otherwise. This is why most references will describe linear search as being ON even though it can be O1 in a best case scenario. So that's the soul of this Big O. Now, algorithm of the third kind. So now we discuss the O1 and ON. Binary search seems to fail somewhere in between O1 and ON. So what is it? In Big O terms, we describe binary search as having a time complexity of O log n. Simply put, O log n is the Big O way of describing an algorithm that increases one step each time the data is doubled. So when your data doubled, let's say from 100 to 200, the algorithm just need to take one step. So less effort with a lot that could handle a lot of data. That's why binary search is faster than linear search. To understand why this algorithm is called O log n, you need to first understand what logarithms are. Now, logarithms, it's from math, are the inverse of exponents. So, in exponents is how the exponential or compound effects work, in which it doubles the number as it goes. So, here's an example. 2 times 2 times 4 times 2, 8 times 2, 16 times 2, 32 times 2, 64. So, that's how compound effect works. Now, logarithm is the inverse of that exponent. So the logarithms of this, since it's 26 translate to this to 64, because we had to multiply 2 by itself 6 times to get 64. Therefore, log base 2 of 64 is equals to 6. So how many times would we multiply 2 to get 64? That is the logarithms. That's the inverse of kind of like measuring how many times you would compound yourself or double the value, like 2 times 2 times 2 times 2, etc. Now that you understand what logarithms are, the meaning behind O log n will become clearer. So O log n explained in computer science, whenever we say O log n, it's actually shorthand of saying O log base 2 n. We just omit the small 2 for convenience. O log n means that for n data elements, the algorithm would take log base 2n steps. If there are 8 elements, the algorithm would take 3 steps, since log base 2 to 8 is equal to 3. Said another way, if we keep dividing 8 elements in half, it would take us 3 steps until we end up with 1 element. Said simply, O log n means the algorithm takes as many steps as it takes to keep having the data elements until we remain with 1. The following table demonstrates a striking difference between the efficiencies of ON and O log n. So, this is how fast is the O log n to On. So remember, it's between O1 and On. So here for 8 elements, it only takes 3 steps, 16 4 steps, 32 5 steps, 64, etc. So while the On algorithm takes as many steps as there are data elements, the O log n algorithm takes just one additional step each time the data is doubled. Practical examples, the first thing to realize is that this is an example of an algorithm. While it may not be fancy, any code that does anything at all is technically an algorithm. It's a particular process for solving a problem. In this case, the problem is that we want to print all the items from a list. The algorithm we use to solve this problem is a for loop containing a print statement. So the first algorithm is actually an algorithm itself. So here, this type of algorithm, though we're just using a simple for loop and then printing it, is an algorithm itself because we're instructing the computer to initiate an action, assuming there's no error, and it actually did what you want to do. So the algorithm we use to solve this problem is a for loop containing a print statement. To break this down, we need to analyze how many steps this algorithm takes. In this case, the main part of the algorithm, the for loop, takes 4 steps. In this example, there are 4 things in the list, and we print each one out a single time. However, the number of steps isn't constant. If the list contained 10 elements, the for loop would take n steps. Since this is for loop takes as many steps as there are elements, we'd say that this algorithm has an efficiency of On. Now the next example is a Python-based algorithm for determining whether a number is a prime. So here we define is_prime function, and then we have parameter number. For I in range 2, and then the number, the parameter that would be entered by the user, we use a if-else statement. If number percentage I is equals to 0, we return false, otherwise return 2. So the preceding code accepts a number as an argument and begins a for loop in which we divide the number by every integer from 2 up to that number and see if there's a remainder. If there's no remainder, we know that the number is not prime, and we immediately return false. So if there's no remainder, we know that the number is not prime, therefore we return a false. So this code actually accepts a number as an argument here and begins a for loop in which we divide the number by every integer from 2 up to that number. So let's say you put 10, we will divide that 10 by 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Now, and see if there's a remainder. So if there's no remainder, we know that that number is not prime, and we immediately return false. If we make it all the way up to the number and always find a remainder, then we know that the number is prime, and we return true. So if we return up to the number, dividing that number from like say example 10, we know that if there's a remainder, we know that it's prime, and then we return true. Here, we're not dealing with an array, but we are dealing with a number that we pass into this function. So as you can see, it's not an array. As you can see, it's a range. We did not use any array here. Here, we're not dealing with an array, but we're dealing with the number that we pass into this function. Depending on the number we passed in, this will affect how many times the functions loop runs. So in this case, then our key question will be, when passing in the number n, how many steps will the algorithm take? So this is actually how we improve the code. So let's say we enter this number n on this code. Let's say we want to improve that based on our company policy. We determine it based on the n elements we entered as an argument to this number. If we pass the number 7 into is underscore prime, the for loop runs about 7 times. So it runs about 7 times because it starts from the 2. Again, 2 divided by 7, 7 divided by 2, 7 divided by 3, 7 divided by 4, 5, 6, 7. So it's about 6. It technically runs 5 times actually. 7, 2, 3, 4, 5, 6. Since it starts at 2 and ends right before the actual number, it actually ends before the actual 7. For the number 101, the loop runs about 101 times because the number of steps increases in lockstep with the number passed into the function. This is a classic example of ON. Again, the key question here dealt with a different kind of n, since our primary piece of data was a number rather than an array. We'll get more practice in identifying our n's as we progress through the future chapters. So here shows us that n, or determining the steps or the n that we put on that function, may not be obvious as an array, because for array you just need to determine the data elements that we need to pass through. We will get more practice on that as we go through. So speeding up your code with Big O. If you find that Big O labels your algorithm as a slow one, you can now take a step back and try to figure out if there's a way to optimize it by trying to get it to fall under a faster category of Big O. This may not always be possible, of course, but it's certainly worth thinking about. So, if you find that your algorithm or function are labeled in a certain category of Big O, you may now check if there's alternatives for you to speed that up. So, for example, a bubble sort, sorting algorithms have been the subject. We're gonna try to find the efficiency and try to improve on that. So let's start with bubble sort. Sorting algorithms have been the subject of extensive research in computer science, and tens of such algorithms have been developed over the years. They all solve the following problem. Given an array of unsorted values, how can we sort them so that they end up in ascending order? In this and the following chapters, we're going to encounter a number of these sorting algorithms. Some of the first ones you'll learn about are known as simple sorts, in that they are easy to understand but are not as efficient as some of the faster sorting algorithms out there. Bubble sort is a basic sorting algorithm and follow these steps. First step, point to two consecutive values in the array. Initially, we start by pointing to the array's first two values. Compare the first item with the second one. If the two items are out of order, in other words, the left value is greater than the right value, swap them because we're trying to make it ascending. If they already happen to be in the correct order, do nothing for this step. Then step 3, move the pointer one cell to the right. Step 4, repeat step 1 to 3 until we reach the end of the array, or if we reach the values that have already been sorted. This will make more sense in the walkthrough that follows. At this point, we have completed our first pass-through of the array. That is, we pass through the array by pointing to each of its values until we reach the end. So we repeat the step 1 to 3 until we reach the end of the array, or if we reach the values that have already been sorted. So at this point, once we're done with step 3, we have completed our first pass through of the array. That is, we pass through the array by pointing to each of its values until we reach the end. So that's the initial pass through, whether we're gonna ship it or we're gonna do nothing. Step 5, we then move the 2 pointers back to the first 2 values of the array and execute another pass through of the array by running step 1 through 4 again. We keep on executing these pass-throughs until we have pass-through in which we did not perform any swaps. When this happens, it means our array is fully sorted and our work is done. Bubble sort in action. Assume we want to sort the array 4, 2, 7, 1, 3. It's currently out of order and we want to produce an array that contains the same values in ascending order. So let's begin the first pass through. This is our starting array 4, 2, 7, 1, 3. Step 1. First, we compare the 4 and the 2. Step 2, they're out of order, so we swap them. Step 3, next, we compare the 4 and the 7. They're in the correct order, so we don't need to perform a swap since 2 is less than 4 and 4 less than 7. They're in the correct order, so we don't need to perform a swap. Step 4, we now compare the 7 and the 1. They're out of order, so we swap them. We compare the 7 and the 3. They're out of the order and swap them. So this is the step 7. So we now know for a fact that 7 is in its correct position within the array because we kept moving it along the right until it reached its proper place. The previous diagram has little lines surrounding the 7 to indicate that the 7 is officially in its correct position. This is actually the reason why this algorithm is called bubble sort. In each pass-through, the highest unsorted value bubbles up to its correct positions. So the highest possible value bubbles in its correct position. So in each pass through, the highest unsorted value bubbles up to its correct position. That's why it's bubble sort. Because we made at least one swap during this pass through, we need to conduct another pass through. Since the swap didn't stop, there's a swap that happened in which the main reason why we're sorting, it means there's still things that needs to be sorted ascendingly. That's why there's a swap. Now, step 8, we compare the 2 and the 4. They're in the correct order, so we do nothing. We compare the 4 and the 1. They're out of order, so we swap them. Again, there's a swap, so that means we need another pass-through. Step 11, we compare the 4 and the 3. They're out of order, so we swap them again. We don't have to compare the 4 and the 7 because we know that 7 is already in its correct position. But because the computer knows it swaps, or the bubble sort algorithm doesn't know it yet, it needs to go another pass through. So that the 7 is already in its correct position from the previous pass through. And now we also know that 4 has bubbled up to its correct position as well. This conclude our second pass through. So you can see in our second pass through, first pass through, the 7 bubble ups to its correct position, and then the second pass through, the 4 bubble ups to its correct position. Because we made at least one swap during the pass through, we need to conduct another pass through. We begin the third pass through. Step 13, we compare the 2 and the 1. They're out of order, so we swap them. Step 15, we compare the 2 and the 3. They're in the correct order, so we do nothing. We know that the 3 has bubbled up to its correct spot again in our third pass through. Since we made at least one swap during this pass through, we need to perform another one, and so begins the fourth pass through. Step 16, we compare the 1 and the 2. Because they're in the order, we don't need to swap. We can end this pass through since all the remaining values are already correctly sorted. Now that we made a pass-through that didn't require any swap, we know that our array is completely sorted. So it went until step 16, in which the array doesn't have to swap anything. So the value is already sorted. So here's an implementation of this in Python. First, we define using def a bubble underscore sort. So as you notice, like we define function using def as in the previous Ruby implementation. Sorry, it's a Python as well, but in Ruby, let's see. Yes, in Ruby it's also def. So that's how we define the function in Ruby. So yeah, so we define a bubble underscore function and a parameter only one, list, and then we start defining unsorted underscore until underscore index is equals to length of the list minus 1, and then sorted initial is false, while not sorted is equals to true, and then for I in range in unsorted until index, if list I is greater than list I plus 1, then list I and then list I plus 1 equals to list I plus 1, list I, and then sorted is equals to false, and sorted until index is minus equals to 1, and then return list. So to use this function, we can pass an sorted array to it like this: print bubble underscore sort, open parenthesis, open bracket 65, 55, 45, 35, 25, 15, 10. Now the first thing we do is create variable called unsorted underscore until underscore index. This keeps track of the rightmost index of the array that has not yet been sorted. So we first create a variable. So that's actually a variable, unsorted underscore until underscore index. This will keep track the rightmost index of the array that has not yet been sorted. So the rightmost, or the part of the array that has not been yet sorted. So when we first start the algorithm, the array is completely unsorted. So we initialize this variable to be the final index in the array. So it's not yet sorted, so we initialize that variable using the last or the final index in the array. Unsorted underscore until underscore index equals to length list minus 1. We also create a variable called sorted that will keep track of whether the array is fully sorted. Of course, when our code first ran, it isn't, so we set it to false. We begin while loop that continues to run as long as the array is not sorted. So while not sorted, or while this is continued to be false, we will run this loop. Next, we preliminary establish sorted to be true. Sorted equals true. So we establish that the sorted to be true. So the approach here is that in each pass through, so inside the while loop, we assume, or we preliminary establish sorted to be true. The approach here is that in each pass through, we'll assume the array is sorted until we encounter a swap. So that's the reason why it's true. Unless there's a swap, therefore it's not sorted yet, in which case we'll change the variable back to false, which is here at the top. Now if we get through the entire pass through without having to make any swaps, sorted will remain true and will end the loop, and we'll know that the array is completely sorted. Within the while loop, we gain there's a for loop in which we point to each pair of values in the array. So for I in range unsorted, we use the variable I as our first pointer, and it starts from the beginning of the array and goes until the index that has not yet been sorted. So it goes until the index that has not yet been sorted, and we use I as a pointer. Within this loop, we compare each pair of adjacent values and swap those values if they're out of order. We also change sorted to false if we have to make a swap. So if we have to make a swap, we also change the sorted to false. So this is actually how we make it back to false, not actually the top sort. But that's the initial parameters. Now within this loop, we compare each pair of adjacent values. So the adjacent values in the I. So as you can see, we swap those values if they're out of order. We compare the two adjacent values and we start at the beginning. At the end of each pass-through, we know that the value we bubbled up all the way to the right is now in its current position. So here, least I is greater than least I plus 1. Therefore, least I, so if it's the initial or the first index is greater than the least I plus 1 or its subsequent index, therefore least I plus 1 is equals to least I plus 1 least I. So we will now sort that, if they're out of order, we will swap those values. So this is how we swap it in Python. At the end of each pass-through, we know that the value we bubbled up all the way to the right, it's now correct position. Because of this, we decrement the unsorted until underscore index by 1, since the index it was already pointing is now sorted. So at the end of each pass-through, we know that we bubbled up some number to the right. So because of this, we decrement the unsorted until underscore index by 1. So therefore, we decrement that initial length of the array so that we could perform the swaps and the comparisons inside that minus bubbled array. So the while loop ends once sorted is true, meaning the array is completely sorted. Once this is the case, we return the sorted array. We return the list. So the efficiency of bubble sort. Our example array has 5 elements. Looking back, you can see that in our first pass through, we had to make 4 comparisons between sets of 2 numbers. In our second pass through, we only had to make 3 comparisons. This is because we didn't have to compare the final 2 numbers, since we knew that the final number was in the correct spot due to the first pass through. So we only need to make 3 comparisons because we didn't have to compare the final 2 numbers in our second pass through, since we knew that the final number was in the correct spot due to the first pass through that we make. In our third pass through, we made 2 comparisons, and in our fourth pass through, in our third pass through, we made 2 comparisons. In our fourth pass through, we made just 1 comparison. So 4 plus 3 plus 2 plus 1 equals to 10 comparisons. To put it in this in a way that would hold true for arrays of all sizes, would say that for n elements, we make n minus 1 plus n minus 2 plus n minus 3 plus 1 comparisons. So in a worst case scenario, where the array is sorted in descending order, the exact opposite of what we want, we'd actually need a swap for each comparison. So we'd have 10 comparisons and 10 swaps in such scenario for a grand total of 20 steps. So this the worst case scenario for this length of array is actually 20 steps. Now let's look at the big picture with an array containing 5 values in reverse order. We make 4 plus 3 plus 2 plus 1 equal 10 comparison. Along with 10 comparison, we also have 10 swap, totaling 20 swap. For such an array with 10 values, we get 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 equal 45 comparison and another 45 swaps. That's a total of 90 steps. With an array containing 20 values, we'd have 190 comparisons. So the efficiency of this is that for n data elements of 5, instead of just n for O of n, it has 20. For 10, 90, 20, 380, 41, 560. If you look the growth of steps as n increases, though 5 squared is not 20, kind of like growing exponentially, or n squared. Take a look at the following table. So it's actually n squared. We just, again, we remove the constant. Number of elements, so a quadratic problem. Here's a practical example where we can replace a O(n) squared algorithm with a speedy one. Let's say we're working on a JavaScript application that analyzing ratings people give to products, where users leave ratings from 1 to 10. Specifically, you're writing a function that checks whether an array of ratings contains any duplicate numbers. This will be used in more complex calculations in other parts of the software. For example, the array 153914 has 2 instances of the number 1. So we'd return true to indicate that the array has a case of duplicate numbers. One of the first approaches that may come to mind is the use of nested loop, as follows. We create a function, so instead of def function, I think it's JavaScript, has duplicate value and an array parameter for let I equals to 0, and then I is less than array.length. So this is what I'm saying. When the computer know the length of the array, we can immediately create that and then use that in our code, such as this for loop. I less than array.length, and then I plus plus, which is increment, and then we create another nested for loop for let j equals to 0, j is less than array.length, and then we increment. Now if not equals to j and array I is equals to array j, return true, and then otherwise return false. In this function, we iterate through each value of the array using the variable I. So we iterate in each array using the variable I that we initiated. As we focus on each value in I, we then run a second loop that looks through all the values in the array using j. So we use another loop using j variable and checks if the values at position j and I and j are the same. So these variable j's are used to check the values at position I and j are the same. If they are, it means we've encountered the duplicate values, we return true. If we get through all of the looping and we haven't encountered any duplicates, we return false, since we know that there are no duplicates in the array. So again, if there are, it means we've encountered duplicate values and we return true. If we get through all of the looping and we haven't encountered any duplicates, we return false, since we know that there are no duplicates in the array. To apply this to our situation, we'd ask ourselves, for n values in the array provided to our has duplicate value function, how many steps would our algorithm take in a worst case scenario? So to apply this to our situation, we'd ask ourselves, for n values in the array provided to our has duplicate value function, how many steps would our algorithm takes in a worst case scenario? The preceding function has one type of step, namely comparisons. It repeatedly compares array I and array j to see if they are equal and therefore represent a duplicate pair. In a worst case scenario, the array contains no duplicates, which would force our code to complete all of the loops and exhaust every possible comparison before returning false. Based on this, we can conclude that for n values in the array, our function would perform n squared comparison, which is exponential compared to just O(n). This is because we perform an outer loop that must iterate n times to get through the entire array, and for each iteration, we must iterate another n times with our inner loop. That's n times n steps, which is n squared steps, leaving us with an algorithm of O(n) squared. We can actually prove it by adding some code and console.log steps in our code. Now function has duplicate, let step equals to 0, count number of steps, for let I again, and then for let j, then step plus plus, increment number of steps, console.log steps. So this added code will print the number of steps taken when there are no duplicate. If we run has duplicate value 14529, for example, we'll see an output of 25 in the JavaScript console, indicating that there are 25 comparisons for the 5 elements in the array. So since this is a worst case, since there's no duplicate, it runs 25 comparison. Now the fact that our function is O(n) squared should give us a pause. This is because O(n) squared is relatively slow algorithm. Whenever you encounter a slow algorithm, it's worth spending some time to consider whether there are any faster alternatives. There may not be any better alternative, but let's first make sure. Finding it or the options available is is better for us than not finding it. So let's see. So a linear solution following is another implementation of the has duplicate value function that doesn't rely on nested loops. It's a bit clever, so let's first look at how it works and then we'll see if it's any more efficient than our first implementation. Now we define the function again, has duplicate value and an array parameter. I think it's still JavaScript. Let exiting numbers equals to an empty array, existing array. So we create a variable here with an array. For let I equals to 0, I is less than array.length, we increment. If existing number array I is equals to 1, we return true. So this is inside the for loop. Else existing numbers array I equals to 1. So we return false. Here what this function does, it creates an array called existing number which start out empty. Then we use a loop to check whether each number in the array, as it encounters each number, it places an arbitrary value. We've chosen to use 1 in the existing numbers array at the index of the number we're encountering. For example, let's say our array 358 is 358. When we encounter 3, we place a 1 at index 3 of existing numbers. So the existing number arrays will now be the rough equivalent of this, like this. So we have an existing number, we created that. So undefined, 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 1, undefined, and 1. So since we have this 3, 5, 8. Now there's now a 1 at index 3 of existing numbers to indicate and remember for the future that we've already encountered a 3 in our given array. When our loop then encounters the 5 from the given array, it adds 1 to index 5 of existing number. So this code is doing that, equals to 1. Array I is equals to 1. Now this code, if existing number array I is equals to actually 1, it means there's a duplicate with another pass-through. So here we put a 1 to track it in the 5th index. Finally, we reach the 8 existing numbers. Will now look like this. Essentially, we're using the indexes of existing numbers to remember which numbers from the array we've seen so far. Now here's the real trick. Before the code stores a 1 in the appropriate index, it first checks to see whether that index already has a 1 as its value. So that's where the first if existing numbers I equal 1, then return true. Else existing number array I just 1 equal to 1 came from. So if it does, this means we've already encountered that number, meaning we've found a duplicate. If this is the case, we simply return true and cut the function short. If we get to the end of the loop without having returned true, it means there are no duplicates and we return false. So if we get to the end of the loop without having returned true, it means there are no duplicates, and we return false. So to determine the efficiency of this new algorithm in terms of, it means we only insert 1 if there's no 1 there. And we return false if we get to the end of the loop with no duplicate 1. So to determine the efficiency of this new algorithm in terms of big O, we once again need to determine the number of steps the algorithm takes in worst case scenario. Here, the significant type of step is looking at each number and checking whether the value of its index in existing number is a 1. So these are the code that consists of a significant number of steps if existing array I is equals to 1. So essentially we're comparing it here. So we need to determine the number of steps the algorithm takes in this worst case scenario. In addition to the comparison, we also make insertions into an existing array, but we're considering that kind of step trivial in this analysis. So the equals to 1, 1 equal to 1 at the end is a trivial. More on this in the next chapter. In that, because I introduce you again that the constants does not really matter as much. In terms of the worst case scenario, such scenario would occur when the array contains no duplicates, in which case our function must complete the entire loop. So it's the same worst case scenario with the 20 results we encounter with the Python code, which there's no duplicate. This new algorithm appears to make n comparisons for n data elements. This is because there's only one loop, and it simply iterates for as many numbers as they are in the array. If we run has duplicate value 14529 now, we'll see that the output in the JavaScript console is 5, which is the same as the size of our array. We'd find this to be true across arrays of all sizes. This algorithm then is ON. There is actually, so this is one of the reasons why code is hard to read sometimes, because this seemingly different codes has the same task that is being accomplished, which is to find a duplicate, which is key. The name of the function is key to determine what function is that. Now, there's actually one disadvantage with this new implementation, namely that this approach will consume more memory than the first approach. Don't worry about this for now. We'll discuss this at length in dealing with space constraints. It's clear that having a solid understanding of big O notation can enable you to identify slow code and select the faster of two competing algorithms. However, there are situations in which big O notation will have us believe that algorithms have the same speed, while one is actually faster. So sometimes a same category, since we ignore constants, would have us believe that it is the same speed, but in more detailed view or more detailed inspection, there's actually more faster algorithm. Now, optimizing code with and without big O. Another type of sorting algorithm is selection sort. Now, the step of selection sort are as follows. We check each cell of the array from left to right to determine which value is least. As we move from cell to cell, we keep track of the lowest value we've encountered so far. We'll do this by storing its index in a variable. So we track the lowest value by storing that in a variable. If we encounter a cell that contains a value that is even lower than 1 in our variable, we replace it so that the variable now points to the new index. See the following diagram. So here lowest value so far is 2, and then lowest so far is 2 again, then lowest so far is 1 now, and then we change the value. Once we've determined the index contains the lowest value, we swap the value with the value we began the pass-through with. So in the next phase of pass-through, this would be index 0 in the first pass-through, index 1 in the second pass-through, and so on. The diagram here illustrates making the swap of the first pass-through. Each pass-through consists of step 1 and 2. We repeat the pass-throughs until we reach a pass-through that would start at the end of the array. By this point, the array will have been sorted. So the main step here is putting the lowest initially in a variable and then comparing until we reach the end of the array. Now selection sort in arrow action. So let's walk through the step of selection sort using the example array 42713. We begin our first pass through. We set things by inspecting the value at index 0. By definition, it's the lowest value in the array we've encountered so far, as it's the only value we've encountered so far. So we keep track of its index in a variable. Lowest value so far is 4, which is at index 4. Step 1, we compare the 2 with the lowest value so far, which happens to be 4. The 2 is even less than 4, so it becomes the lowest value so far, so we swap it. Step 2, we compare the next value, the 7, with the lowest value so far. The 7 is greater than 2, so 2 remains our lowest value, we do nothing. Step 3, we compare the 1 with the lowest value so far, which is 2. Because 1 is even less than 2, 1 becomes our new lowest value. Step 4, we compare the 3 to the lowest value so far, which is the 1. We've reached the end of the array and determined that 1 is the lowest value out of the entire array. So as you can see, we're not swapping it yet, we're just comparing. Because 1 is the lowest value, we swap it with whatever value is at index 0, which in this case is 4, the index we began this pass through with. Since we've moved the lowest value to the beginning of the array, that means the lowest value is now in its correct spot. We're now ready to begin our second pass through. Set up, the first cell index 0 is already sorted, so this pass through begins at the next cell, which is index 1. So we know that first index is already sorted, therefore we will start with index 1. The value at index 1 is the number 2, and it's the lowest value we've encountered so far. Step 6, we compare 7 with the lowest value so far. The 2 is still less than 2, so we do nothing. Step 7, we compare the value 4 with the lowest value so far. The 2 is less than the 4, so 2 remains our lowest value. We compare the 3, so we store that in the variable. Then step 8, we compare the 3 with the lowest value so far that we stored, which is 4. The 2 is less than the 3, so 2 remains our lowest value. The 2 rather. So we've reached the end of the array. Since the lowest value from this pass through is in correct spot, we do nothing. We don't need to perform a swap. This ends our second pass through, leaving us with 12743. We now begin the third pass through. Set up, we begin at index 2, which contains the value 7. The 7 is the value we've encountered so far. In this pass through, we store that in a variable. We compare the 4 with 7. We know that 4 is our new lowest value, but we don't perform the swap yet again. We encounter the 3, which is even lower than 4. The 3 becomes our new lowest value. So we swap that with 4 in the variable, but we're not actually conducting swap yet. Now step 11, we've reached the end of the array. So we swap 3 with the value we started our pass through, which is 7. We now know that 3 is in the correct place within the array. So which starts with index 3, which is where the 4. While you and I can both see that the entire array is correctly sorted at this point, the computer does not know this yet, so it must begin a fourth pass through because the variable needs to be sure and track it in the variable for more consistent applications to all of the arrays that we are using this algorithm. Now step setup, we begin pass through with index 3, which is 4. The lowest value so far. We compare the 7 with 4. So step 12, we compare the 7 with 4. The 4 remains the lowest value we've encountered in this pass through so far, so we don't need to swap it since it's already in the correct place. Because all the cells beside the last one are correctly sorted, that must mean the cell is also in the correct order and our entire array is properly sorted. So that's the exception. If the last cell is, we don't need to sort the last cell because the computer could program it in which the last cell doesn't need to be sorted. Now here's the code implementation using JavaScript. We initiate a function, selection, sort, and then array as parameter, as a one parameter. We created the for loop. Again, let I equals to 0, starts with a 0, and then the array dot length -1, and then I plus plus. Now let lowest number index is equals to I first, and then we create another nested for loop for let j is equals to I. So we equate that to a in this nested for loop, and then j is less than array dot length without -1, and j plus plus increment. Now if array j is less than array lowest number index, then lowest number index is equals to j. Now if lowest number index is not equals to I, let temporary is equals to array to I, array I, and then array I is equals to array lowest number index, and array lowest number index equals to temporary. Then return array. So here's the each line by line explanation. We begin the loop that represents each pass through. It uses the variable I to point to each value of the array. So it uses variable I to point to the each index in the array and goes up through the second to last value at initial for loop. It doesn't need to run for the last value itself since the array will be fully sorted by that point. So that's the meaning of this for loop. Next, begin keeping track of the index containing the lowest value we encounter so far. Notice this programming language. This has been created by computer scientists before. So all you need to do is to study this way of solving this problem. Maybe you can apply it kind of like in design patterns and principle. Someone already created that, so you can just build on top of that to solve new problems, because it's really hard to create this. It took them years for them to discover or develop this algorithm. Now it doesn't need to run for the last value itself since the array is fully sorted by that point. Next, begin keeping track of the index containing the lowest value we encounter so far. So this is where we track that in the variable let lowest number equals to I. This lowest number index will be 0 at the beginning of the first pass through, 1 at the beginning of the second, and so on. The reason we specifically keep track of the index is because we'll need access to both the lowest value and its index in the rest of our code. So the reason why we need to create this variable is we need to keep track of the index and its value, and we can use the index to reference both. So we can use this index lowest number index equals to I to reference the value and the index position. We can check the lowest value by calling array lowest number index. So within each pass through, we check the remaining values of the array to see if there might be a lower value than the current lowest value. So since we stored that already, so this is actually where we check the other part or index of the array. We check that using the for loop j. For let j is equals to I plus 1, and then j is less than array dot length. So since we added the 1, therefore we don't need to -1, and then we increment it. Indeed, if we find a lower value, we store this new values index in lowest number index. So if array j we find from this for loop is less than array lowest number index, which initially store here to keep track of the index and the value, therefore lowest number index should be equals to our now new find variable, which is j, to point to the index. By the end of the inner loop, we'll have found the index of the lowest number from this pass through. So by the end of this inner loop, we will found the index of the lowest number from this initial pass-through. If the lowest value from this pass-through is already in its correct place, which would happen when the lowest value is the first we encounter, we don't need to do anything. But if the lowest value is not in the correct place, we need to perform a swap. So this is where the swap code. Specifically, we swap the lowest value with the value at I, which was the index we started the pass-through with. So if lowest number index is not equals to I, let temp equals to RAI, and then RAI is equals to RA, lowest number index, and then RA, lowest number index equals to temporary value. So we change the lower number index. Finally, we return the sorted array. Now the efficiency of selection sort. Selection sort contains two types of steps: comparison and swap. That is, we compare each value with the lowest number we encountered in each pass-through, and we swap the lowest number into its correct position. Looking back at our example array that contains 5 elements, we had to make a total of 10 comparisons. Let's break it down in the following table. For first pass-through, 4 comparison; second, 3; third, 2 comparison; fourth, 1. That's a total of 10 comparison. To put it in a way that works for all array, we'd say that 4 n elements would make n minus 1 plus n minus 2 plus n minus 3 plus 1 comparison. As for swaps, though, we only need to make a maximum of 1 swap per pass-through. This is because in each pass-through, we make either 1 or 0 swaps, depending on whether the lowest number of the pass-through is already in the correct position. Contrast this with bubble sort, where in worst case scenario, an array in descending order, we have to make a swap for every comparison. N elements is 5. Max number of steps in bubble sort, 20. Max number of steps in selection sort is 14. So for 10 elements, 90 for bubble sort and 54 for selection sort. 20, 30, 380 for bubble sort and 199. So it means like it's almost half of the bubble sort, or the n squared. Now ignoring constants, so this is what we're saying when we want to ignore constant. Again, big O notation answer the key question. If there are n data elements, how many steps will the algorithm take? Because selection sort takes roughly half of n2 steps, n squared steps, it would seem reasonable that we describe the efficiency of selection sort as being O(n) squared over 2, because it's divided by 2. That is, for n data elements, there are n squared over 2 steps. The following table bears this out. In reality, however, selection sort is described in big O as O(n) squared, just like bubble sort, because we're categorizing it on that part. No matter how the constant 1 have multiplied it, it doesn't matter in the end, because as the data increases, it differentiates it enormously from O log n, O(n), and O(n) step. This is because of a major rule of big O that I'm now introducing for the first time. Big O notation ignores constants. Even O100n, which is 100 times lower than O(n), is also referred to as O(n). Offhand, it would seem that this rule would render big O notation entirely useless, as you can have two algorithms that are described in the same exact way with big O, and yet one can be 100 times faster than the other. And that's exactly what we're seeing here with selection sort and bubble sort. Both are described in big O as O(n) squared, but selection sort is actually twice as fast as bubble sort. So this is where a big O would make you believe that two same algorithms has the same speed, although in more detailed inspection, some are actually twice faster. So big O categories, if we were to compare two buildings, one which is a single family home and one which is a skyscraper, it becomes almost moot to mention how many floors each one has, because the two buildings are so incredibly different in their sizes and functions. We don't need to say this one is a 2-story home while the other is a 100-floor skyscraper. We may as well just call one house and other a skyscraper. Calling them by their general categories is enough to signify their vast differences. Therefore, when comparing two efficiencies that belong to two different categories of big O, it's enough to identify them by their general category. talking about O2n when compared to ON squared is like talking about a two-story house compared to a skyscraper. We may as well just say that O squared, O2n is part of the general category of ON. All the types of big O we've encountered, whether it's O1, O log n, ON, ON squared, or the types we'll encounter later in this chapter, are general categories of big O that are widely different from each other. Multiplying or dividing the number of steps by a regular number doesn't make them change to another category. However, when two algorithms fall under the same classification of big O, it doesn't necessarily mean that both algorithms have the same speed. After all, bubble sort is twice as selection sort, even though both are ON squared. So while big O is perfect for constructing algorithms that fall under different classification of big O, when two algorithms fall under the same classification, further analysis is required to determine which algorithms is faster. For us to see it in further inspection, a practical example. So the print, we define a print underscore number version 1 up and then upper limits as a parameter, and then we initiate a number as an equals to 2. Now while number is less than or equals the upper limit, if number is even, print it. So here, I think we've discussed this in the first chapter. So here we have two algorithms for accomplishing the same task, namely printing all even numbers starting from 2 to some upper limit. In chapter 1, the upper limit was fixed at 100, while here we let the user pass in a number as the upper limit. Now the first version takes about n step, that is, the upper limit is 100. The function takes about 100 steps. So the first functions or algorithm we analyze based on its data, structure, and its algorithm speed in the first chapter actually doesn't has the same category in big O, but in further inspection it's just different with its constant. That is, it is multiplied by 2, or one is twice faster than the other. Now the first version takes about n steps, that is, the upper limit is 100. The function takes about 100 steps. It really takes 99 steps since it starts the count as 2. So we can safely say that the first algorithm has a time complexity of ON. The second version, n over 2 steps. When the upper limit is 100, the function takes just 50 steps. Well, it would be tempting to call this ON over 2. You've now learned that we drop the constants and reduce the expression to ON as well. So significant steps. Let's apply one more level of analysis to the previous example. If we look again at the first version, print underscore numbers underscore version underscore 1, we said that it takes n steps. This is because the loop runs n times, with n being the upper limit. But does the function really take just n steps? If we really break things down, we can see the multiple steps occur in each round of the loop. First, we have the comparison steps. If number %2 equals to 0, which checks whether the number is divisible by 2, the comparison happens in each round of the loop. Second, we have the print step, print number, which happens just for the even numbers. This then occurs in every other round of the loop. And third, we have number plus equal 1 step, which runs in each round of the loop. In the previous chapters, I alluded that the fact that you learn how to determine which steps are significant enough to be counted when expressing the big O algorithm. In our case then, which of these steps are considered significant? Do we care about comparison, the printing, or the incrementing of number steps? Let's apply this here. If we count all the steps, we have n comparisons, n incrementings, and n over 2 printings. This add up to 2.5 n steps. However, because we eliminate the constants of 2.5, we express this as ON. So which step was significant? They all were, but by dropping the constant, we effectively focus more on the number of times the loop runs. So we're focusing on the number of times the loop runs instead of each step on inside that loop, rather than exact details of what happens within the loop. So that's actually what the big O category represents. We now have some powerful analysis. To letter disposal, we can use big O to broadly determine the efficiency of an algorithm, and we can also compare two algorithms that fall within one classification of big O. So up until this, we discussed how to determine the worst case scenario, efficiency of steps. In the later chapters, we will discuss as well the best case scenario and compare that. So here, optimizing for optimistic scenario.